Okay, thanks. So, right. So today, I wanted to present this work I've discussed with some of you already. So I thought, okay, why not presenting it to the lab? So this was a work published last year with Alberto Rosso in IPhT-TV and Denis Basco and Marcus Osman in Grenoble. So, okay, please interrupt whenever you want. I try to be pedagogical, but okay, don't hesitate if you have questions. Right. So first, I will talk about two examples. I will take examples of systems that have localization induced by a bath. So in this sense, I will specify what localization means. So maybe the most well-known model is the spin boson model. So basically, the idea is that you take a single particle in a double well structure here. So here you can see the energy levels with the corresponding wave functions. Okay, and well, you can see that if you have almost symmetric double wells, you have due to tunneling, you have that the wave function is spread on both wells. And the idea of the spin boson model is basically to couple this particle to a bath of, let's say, harmonic oscillators. That's the term here. And you want to look at properties at very small temperature. So basically, you focus on only the two lowest levels here, those ones. And then you have this so-called spin boson Hamiltonian that I brought here on top. And so basically you just have a two-level system, just two levels, which is described by a few parameters. For example, this delta here is basically the difference between the two energy levels between the two wells. And this delta zero here is the tunneling amplitude of the two-level system. And okay, you have coupled it to a bath of bosonic operators. And it is specified, basically the distribution of modes is specified by this spectral function that extends down to zero energy and goes like omega to the power s. And what is known in this model, basically what you can do is there are many ways to do it, but what you can do is you can try to integrate out the bath degrees of freedom and to see how they would renormalize the parameters of the two-level system. So you get a flow equation, and what you can show is that for s less than 1, basically this the tunneling amplitude vanishes. So this means that you have localization in one of the two wells. So basically where you start, because you don't have any more tunneling. You stay quenched in one of the two wells. So okay, this is maybe the most well-known example. And there is also, you can extend it for a many-body system. So for example, here in the X6Z model, here, okay, this has been done in several recent works, including one by Laura. And okay, basically that's the same idea. You couple the X6Z model to a bath of harmonic oscillators, and the bath is still described by this spectral function with omega to the s. And well, what you can see, okay, you can analyze it exactly at zero temperature by doing bosonization. So this means that basically you will fill all the energy levels below the Fermi energy, and you will linearize the Hamiltonian close to Fermi energy. And this makes you turn the degrees of freedom, the spins, into bosonic modes, and you can write a field theory for them and analyze it. And basically what has been found here is that when you increase here the coupling to the bath, you go from a Luttinger liquid phase that is perfectly conducting to a dissipative phase where you don't have transport anymore. So it's not conducting anymore. So it's localization in the sense that you are here you can see that you are inhibiting transport. Okay. Okay. All this is at zero temperature. Right. So there are other examples. I will talk about one another later on, but I will first introduce the model before. So, okay, to be able to talk about thermalization in contact with a bath, I will first have to deal with thermalization in isolated systems because it's very important for the following. So I just recall the two ingredients that you need for a quantum system isolated to thermalize. So it's isolated, so you have basically it's described by the Hamiltonian and its eigenstates here. And okay, the first ingredient is dephasing, right? So if you look at the density matrix, the time evolution of the density matrix, basically if you project it in the eigenstate basis, you'll have that the off-diagonal elements, they will oscillate. So these are the so-called coherences of the system. They oscillate while the diagonal remains constant. Okay. And now if you take, actually, so all this has been discussed by Mark Strelnicki in September when he was talking about eigenstate thermalization hypothesis. So now if you consider the temporal average of some observable, so you are thinking of a steady state, you want to make thermal averages. So you will compute these averages and you see that due to the fact that you have oscillating behavior here, it gets projected on the diagonal, so on the eigenstates of the Hamiltonian. Okay. So this is the so-called dephasing. And the second ingredient is that here you can see the matrix that is, I mean, the diagonal element in the of any observable A. And so the second ingredient is that this is the so-called eigenstate thermalization hypothesis, is that those diagonal elements, they should be, so they are typical of some energy that you have fixed. You are in isolated systems, you are in the microcanonical situation. So you fix the energy, and every eigenstate at this given energy, approximately, they are typical. So this means they are exactly matching the microcanonical value that you expect at this energy. Okay. And if you plug this into this, you will have exactly right away the fact that the temporal average is equal to the thermal average. Okay, so that's the idea for thermalization in quantum systems. Now another thing, it's just a feature of thermalizing system, isolated system, that I have to define a bit because I will use it later on, is the so-called entanglement entropy. So the idea of the entanglement entropy is that, okay, you have the isolated system, let's say it's in some state psi, okay? Let's say an eigenstate, for example, whatever. And the idea is that you subdivide the system into two components, A and B, and you will trace over the part B, and then you can look at the reduced density matrix of the system and compute its standard von Neumann entropy. So that's called the entanglement entropy. And what you expect is that an isolated system that would thermalize would be some kind of would act as its own bath. So if it's thermalizing, then this entropy would be extensive in the system size. Okay, and this is what you see. For example, here I take this example that is famous in the literature. This is a Heisenberg model with a random field. Okay, and what you see is that if you have strong enough interactions, you get that indeed the entanglement entropy. So that's here plotted divided by the system size L. Okay, where they traced half of the system. You see that it's extensive here in when you are increasing the system size, while if you don't have enough interactions, you don't see anymore this extensive behavior. This is usual of many-body localized states here, for example. Basically, you are dominated by this independent Hamiltonian. Okay, so right, so maybe the theoretical question we asked in this work is that well, if you take a generic experiment, what you expect is that the system satisfies ETH, and we know that there are dephasing processes. So there is the one I was talking to you about, but there is also the dephasing process due to the bath. So I mean, it should be thermalizing. So the question we ask is, can we avoid thermalization in an ETH system that is coupled to a bath? And as I told you, The only missing part here is that if you want to not thermalize, you have to examine what happens in the dynamics when you couple it to the bath. Because without the bath, it's already thermalizing by itself. Okay, so this is kind of a theoretical question, but we asked ourselves this question because we were actually interested in an experiment, an experimental setting, which is an experiment in nuclear magnetic resonance. It's actually a protocol which is called dynamic nuclear polarization. So now we'll introduce what it is, because this is basically the setup we have in mind. And this is actually, actually it's a good coincidence to be here, because it was a field that was pioneered by Anatole Abragam, and we are in the Abragam building, so it's maybe a good occasion to make a talk about this. I just mentioned that, don't be lost if sometimes I use polarization, the word, because what I mean is just magnetization. So, for example, magnetization on the z-axis. So I tend to use both words interchangeably, so don't be confused about that. Okay, so what's this dynamic nuclear polarization experiment? So the idea is you want to polarize nuclei, for example, organic matter. So you have a lot of, let's say, carbons or hydrogen, and you want to polarize the nuclei of those species. So the thing you may think about firstly is that, to polarize the spins, I can just put a very extremely low temperature, typically 1 Kelvin, and an extremely high field, so for example 3 Tesla. And by doing so, I will have this I will have the interaction of the spin 1/2 with a magnetic field. So I will have some gap of this nuclei. And so we'll have polarization that is given by the Boltzmann law, that is this quantity here. But if you do that, even though you have extremely low temperature, a very, very high field, you have very weak polarization of the nuclei. So the idea that people have come up with is actually to dope the system with electrons. So you dope the system with some molecules that have 3 electrons. And the system of electrons, you will irradiate them through microwaves, so that the microwaves kind of put them in an out of equilibrium state. And those electrons, they are interacting with each other. So basically they thermalize, and they thermalize to a given temperature that you can actually tune with the microwaves. And then by hyperfine interactions between this gas of electrons and the nuclei, they will transmit the temperature, so they will thermalize the nuclei. And they do so at their own temperature, which is called the spin temperature. So now you are thermalizing not at the temperature of the experiment, let's say 1 Kelvin, but at the temperature of the electron gas. That you can tune. Here you can see you can tune it with, let's say here, with a microwave frequency. You can tune this temperature so that you can get a good polarization. Here, for example, here it's the maximum polarization you can get of the sample of the nuclei. And it works very well, because instead of being 1 Kelvin, you are typically at millikelvin range. So you lower the temperature by a factor 1000 just by doing this. Right, so that's the idea of this NMR protocol.
Sorry, the
yes.
spin temperature, how is it measured?
How is it measured? That's a good question. They know how to measure.
One, right?
Sorry?
It's an effective one.
Yeah, so basically what they know how to measure is the temperature of the nuclei. The temperature of the electrons, it's a bit harder, but there are ways to actually, in the next slide, I will tell you how you can. There are ways to measure both temperature. For example, the temperature of the hydrogen, of the carbons, and also for the electrons, it's a bit more difficult. And you see that it's a well-defined temperature, because if you measure both hydrogen and carbon, they have the same effective temperature. So it means that this is the gas of electron that thermalizes them. Okay. Right. That's everything I wanted to say. So. Right, so this is the typical thing that experimentalists know how to measure. It's called the electron paramagnetic resonance spectrum. Okay, so it's a complicated observable. I don't want to define. I don't want to define it. It's just a spectrum that you can measure in experiments for the electrons. Okay, and typically you see two shapes of this spectrum. The first one is okay, if the electrons are in thermal equilibrium, which in the field they call that thermal mixing. So you are equilibrated at some spin temperature beta s, okay, and instead of having this Boltzmann kind of Gaussian, so that's typical of the Boltzmann temperature, you have this profile with a line close to irradiation. So this is the frequency of irradiation of the microwaves. You have this kind of line here, and it's typical of thermalizing. That's how you can measure it. And if it's not thermalizing, what you would typically have is this hole burning shape instead. So this is the case, for example, if you look at non-interacting electrons, that's block already that studied this system, or many body localized system. So what it means here is that you don't have a single temperature for all the electrons. You have kind of each electron goes to its own temperature, and it doesn't define a thermal state. That's why basically close to here you have this shape, which means that basically you are going to very high temperature, while here you are more close to the Boltzmann temperature, which is very cold. Okay. Right. Anyway. So you have those two shapes. So what we had at the time is that we had kind of indirect evidence that if you raise the temperature, so I was talking about the reference state for thermal mixing is kind of 1 Kelvin, something like that. And what you see in experiments is that if you increase the temperature above 4 or 5 Kelvin, you have some indirect proof that you don't see anymore this thermal mixing behavior. And so we thought that it would be some kind, so just by raising temperature. So it must be some kind of ergodicity breaking that is induced by the coupling to the bath. Okay, so that's the idea. Now I'm going to present, the model we use for this protocol. And I will talk about the crucial thing here, which is the dynamics in contact with the bath. So okay, this is the model of the experiment, if you want. So basically, you have 3 ingredients. The first one is that okay, you are doing NMR experiments, so you have this very strong magnetic field at 3 Tesla, which is basically on the z-axis. So it's represented by the static field here, coupled to the SIZ operators. And it's the same for everyone. And it's very, very large. It's the largest unit of energy in the system, because it's basically a very high magnetic field. And actually, due to the fact that it's very large, and to the fact that each electron is kind of hosted by a molecule that has kind of disordered orientation, can be from one side to the other, it changes. You have some kind of anisotropy that results in a bit of a small disorder in the magnetic field. So you have the strong disorder from the field, and also due to non-inhomogeneity of the sample, this kind of disorder that we model as just a random field disorder with some strength delta omega e. Okay, so that spreads a bit the magnetic field. So if you represent on this axis on the energy, you put all your spins on this energy. They are typically at energy omega e plus some spread in the magnetic field. So each one has a different local field. Okay, and then on top of that, the spins, they interact with the electron spins, they interact with each other, otherwise there wouldn't be any thermalization through dipolar interactions. Okay, and when you have a strong magnetic field, it becomes of this form. So this is basically spin flips Hamiltonian, and again, the dipolar interaction depends on the distance with each other. So basically, in those kind of samples that are a bit disordered and glassy, the distance is a bit random, so we model it by just a Gaussian random interaction with some strength u. Okay. And the thing to have in mind in terms of energy scales is that this big magnetic field is much larger, like 1,000 times larger in interaction, compared to the interaction and the disorder, which are roughly of the same order of magnitude. One thing that you can notice maybe is that if you look at the total polarization along the z-axis, it is conserved by this Hamiltonian. And it's a physical consequence of having a strong magnetic field along the z-axis. So I don't have just energy that is conserved, I also have polarization in this Hamiltonian. And of course, you have to put the microwaves to get this spin temperature behavior. So the microwave is just standard. It's just a microwave field that is rotating in the xy axis, and with some amplitude omega 1, which is the smallest energy scale in the problem, basically, and some typical frequency omega microwave. Okay, so yeah, typically it will resonate with some spins here, for example.
And so just the uij is average, uij, it's not uij squared.
Yeah, sorry, yeah, it's this is the variance. Sorry, yeah, it's
and the average is 5 to 0.
Yeah, it's a 0. Yeah, it's just so you take random interaction, it can be any sign. And so, but the crucial thing is that its order of magnitude is given by u, basically. Yeah, so it's there is a square. Okay, so what this Hamiltonian of the spins alone means is that, okay, you have, if you look at the spectrum, it looks like that. You have packets of given polarization. And then if you flip a spin, you get an increase of basically omega e in energy. So you will go from this sector of polarization to the upper one here. And within each sector, you have a large, I mean, it's a many-body system, so you have a large number of energy levels with a spread that is basically given by the interaction and the disorder. Okay, so that's what it looks like. And here I will put myself in the case where there is ETH is satisfied, so the electrons are thermalizing, which you can check by again doing this ETH check. For example, for the diagonal, you take any spin, any electron spin along the z-axis, and you measure its typical value in an eigenstate n. And I will be in the case where, like this yellow case here, where here. So for example, this is done for all the eigenstates that are at in the zero polarization sector. So you expect that basically every spin will have zero magnetization, and this is what you see here. Everything is typically concentrated on the zero value, which is not the case if you have a larger disorder. If you have a larger disorder, you have each eigenstate fluctuates between plus or minus 1/2. So now I'm thermalizing, so I just take this situation here. So this means strong enough interactions. Right, and now I have to talk about the bath. So the bath is, so okay, I have my electron spins, and they are embedded in this kind of sample, glassy sample, okay? And actually there are not many of them, it's just a doping, and they are very, very dilute. So basically, the bath here is just the vibrations of the lattice, the phonons. And the crucial assumption that I need for the physics of the system that I'm going to show is that basically each electron spin has its own bath, so that's all the vibrational modes are spatially uncorrelated, which you can think of, I mean, which is quite natural in the system because you can think of having this property in two ways. Maybe if I have time, I will talk a bit about how we model the bath, but yeah, maybe not. Well, in a glassy system, you have vibrations that can be spatially localized, so that's a natural thing to consider here. But also, if you consider just the phonons that are always there, acoustic phonons, they will. The fact that spins are very dilute, this means that you have large distances between the electron spins, and the phonons they will decorrelate on large times. So basically, I need those modes of the bath to decorrelate spatially between each spin. So the interaction of the what we can show in this situation is that the interaction that I'm taking in the following is typically you couple all the spins with some vibrational modes, bosonic modes here. Okay, right now, this is the crucial part for the dynamics. So, so how do we model this dynamics with interaction with the bath? Basically, what we do is that we consider, and this is actually a good approximation because this system has been studied before in this range. What we do is that we try to trace over the bath degrees of freedom to get an evolution equation for the reduced density matrix of the spins. And if you take the Markovian approximation, so this means that the bath, the correlation functions of the bath relax quite quickly with respect to the relaxation time of the system, which is quite natural in plastic systems and stuff like that. If you make this assumption, then you have a sort of theorem that tells you that the density matrix of the spin system, once you trace over the bath, has this Gorini-Kosakowski-Sudarshan-Lim platform, which is made of a unitary part, so like in the Liouville-von Neumann equation, with some Hermitian operator here, H, plus other terms here, which is not in the unitary fashion, so which is composed of those A alpha, which are called jump operators. So basically, those are operators that kind of flip a bit the spins to exchange energy with the bath. And this is, I mean, it must be of this form if you make the Markovian approximation. The problem is that I know that there is this form. How do I get it from the microscopics? So I trace over the bath, and I have to get this form. And this, in general, there is no way to do it, the perfect way to do it. So the way we do it here is we consider that the bath is weakly coupled to the system, and you can have then this weakly coupled Born equation in which you trace over the bath degrees of freedom, and basically you get this equation if you are doing a perturbation in the interaction of the system. And at second order, for example, this equation is exact. At second order, it's exact. Okay, this is the Boltzmann distribution of the bath, and this is your density matrix for your system. And here you have the interaction that comes in, and this is exact at second order. Now the problem is that you see it's not Markovian. Okay, it depends on all the history of the system. And the thing is how do you do then the Markovian approximation? And all right, you have several ways to do it, and the usual one is okay. You could just neglect this dependence here, but then if you do that, you don't have a form like that, a Lim platform. So you have to make another approximation, which is usually called the secular approximation. So you have basically to throw some terms here. Okay, you throw some terms so that it becomes a well-defined equation of motion for the density matrix. The problem is that if you do this, so this so-called secular approximation, the problem is that this secular approximation, it always projects the system at long times on the eigenstates of the Hamiltonian, which is fine if you want things to thermalize, but here we are considering a more general case. So the problem of this approximation is that it makes the system thermalize no matter what. Okay, I will come back to this a bit later. And another problem is that when you throw terms in this, you typically throw terms where, I mean, it's usually justified if the gaps of the systems are very big, but for a mini-MOD system, this is not true. For example, here the gap between two polarization sectors is big, but within a sector you have gaps. I mean, you have degenerate, non-degenerate eigenstates, and the gap between each other is exponentially small in the system size. So this secular approximation does not not justified, and actually that's what we do to get a better dynamics, is that we keep those gaps, the description of those small gaps. So, right. So, okay, I deal with the first example to try to explain what happens. So it's an example where we know how to solve analytically things, and then for larger n we don't know. But now if you just take 2 spins, okay, so you have just 4 levels. Well, we can try to solve the problem. And actually there is a way to make it solvable, is that instead of, okay, you take 2 spins and you irradiate only one of the 2 spins. So spin 1 will get the microwaves. And then what you do is that you truncate. Actually, you don't consider you just consider the 3 lowest levels, because the highest one doesn't do anything in the physics here. And you couple the system to a local bath of standard bosonic modes. And okay, the situation is here, so I'm trying to reconnect with what I told you for the Hamiltonian. Basically, you have a ground state, which would be spin down spins, okay? And you have the 2 states here, which are basically the untangled spin 0 states, where you have, okay, omega E energy minus delta, so basically the disorder, and another one at omega E plus delta, and you have some interaction between the 2. So sorry, this is called J here, but it was U before. And you put the microwaves only on the first spin, so this means that basically you have the microwaves kind of want to balance the population between the ground state and the state 1, okay? And it's connected to a bath that, okay, for simplicity, you take it at 0 temperature, so the bath just want to dump the population down to the ground states, okay? And then what you can do is really simple. You can just take this equation, make the Markovian approximation as you would do usually, so naive one, in which you make it, in which you disregard the tau, basically the evolution on this tau variable here. So because you say that things decorrelate, etc. And then you can simplify a bit everything. You just take the inputs of the problem, that this energy scale is super large, so then you have few operators that comes in. And you treat the microwaves in perturbation, so in perturbation the amplitude of the microwave. And then you can have the steady state of the system, which I plot on the right. So you can look at the population of level 1, so it's this red thing, rho 1, 1, and the population on level 2, rho 2, 2. So basically the physics is that what you expect is that, okay, there is the bath that wants to populate the ground state. And then you have the microwaves that try to balance the population and to make this state populated. So this state should be depopulated, but due to the interaction, it kind of shares the population with state 1. So in the case where you are ergodic, so in the case where basically the interaction is big, what you can see is that both populations are the same here. So you have the same curve. So sorry, this here, in function of the microwave frequency here, the x-axis, okay? And so this means that the interaction balances the population as you would expect for something thermal, okay? You are putting the microwave on one spin, but it shares the energy with the other spin. And what happens is that if now it's the coupling to the bath that becomes a strong scale in the system, then you have this here where you see that actually it's the level 1 that gets populated and not the other one, as if the interaction was not strong enough to balance the 2 levels. Okay, and here in the middle is just the Anderson case where you take like very big disorder, and then the two states don't talk to each other, and they are quite separated. Okay, so right, I will come back to this a bit later, but that's a bit the idea so far. So we know how to solve this, but but in general, for n larger than 2, we don't know how to do this. So for n larger than 2, we had to use a convenient Markovian description, which is the one that was actually we took this one that was published recently by Nathan and Rodner, which is very nice because basically it takes into this. I mean, you're not throwing any terms anymore. You're just doing the macrodynamic approximation, but not in the naive way I was telling you about before. In some more complicated way. But in the end, you recover a kind of Lindblad equation without having to throw terms away. Okay, you're not throwing anything, not like the circular approximation. So what is this equation? So this equation is, okay, so you have this unitary part I was telling you about before. So here you have the spin system Hamiltonian, okay? And then here it's due to the microwaves, okay? Omega 1 is the amplitude of the microwaves, and omega microwave is the frequency. And okay, you see that the microwave evolution here is static, okay? It's because basically here I'm considering the density matrix which in a rotating frame which rotates in the xy plane with the microwave so that it renders everything static. Okay, so that's just the effect of rotating the density matrix. And then you have this important part with the jump operators, okay, and you have and in this prescription what you get is that it looks like this. So it's a sum over all the possible eigenstates of the system. Here you recognize SI mu, which is the local operators that were coupled with the Bath. And here you have functions of omega and m, which are the gaps, all the gaps of the system. This h here, okay, it's not really useful. It's just, well, it's just something that ensures the type balance at some temperature beta, okay, which means that if you don't put the microwaves, you would go to the Boltzmann equilibrium at temperature beta. And here you have a time scale actually. So this is a time scale of the Bath that you have to compute with the microscopics. And so it's really a time scale, a relaxation time scale of the Bath at some energy omega and m. Okay. So what this means in this system is that you have basically two time scales. You can have transitions from okay, you can have spin flip transitions. So for example, XY operators that would basically change polarization, so pass from one eigenstate to another group here. And basically this is called T1, so this is the T1 scale, so that's the typical time scale for this transition. And then you have the time scales of SZ transition that stays in the same group of polarization. And you can call it another way, T star, let's say, so you can have two typical time scales. Okay, of course you can have zero energy transitions. Very important. Okay, and the thing I want to say about this equation is that if those timescales of the Bath they become long, okay, then you recover the circular approximation. So that's the one I was talking to you about, which means that if you look again as I did before, if you look at this equation in the off diagonal of the Hamiltonian basis, okay, of the eigenstates, then you get this exact equation, which means that the coherences they get exponentially damped, and they go to zero, and then this means that your density matrix is projected on the Hamiltonian eigenstates, and what you expect in this case is that due to ETH, it will have a thermal behavior. While okay, so this is where timescales become long, but in the general case, here you can see that you can simplify a bit if you say that the relaxation timescale they don't depend much on the energy. You can see that basically these jump operators they become local in the spin basis they become local in space. So just a combination of SI plus, SI minus, or SIZ. Okay, and this is very important for the rest. Right, okay, I will skip this because I don't think I will have time, but just to say that now what you have to know is, okay, I have to tell you how to compute those relaxation timescale. So in general, I don't know how to do it. For example, if we consider glassy localized vibration, I don't know how to do it. But I know how to do it if I consider phonons, okay? And if I consider phonons, I can, so this is the definition, okay, of this quantity here. It's just the Fourier transform or Bath correlation functions, okay? And basically, okay, we have a model in this case where, due to the dominant interaction in the system, which is the magnetic field, and if you consider how this is affected by the propagation of phonons, basically you have a process which is called the Raman process. That is basically you exchange, to get energy omega, you exchange two phonons. And what you get, the important thing I want to stress is that these timescales at energy omega, they become proportional to beta square, which means that at low temperature timescales are long, and at high temperature timescales are short, which is quite, okay, natural. But it's also good because it's, for the few things we have in experiments, it's how timescale evolve in these experiments. So, but the crucial point is that at high temperature they become short, and at low temperature they become long. Okay, so now I'm trying to explain a bit the physics of what happens. Okay, so I have this equation, this Lindblad equation, so a unitary part and a dissipative part, basically. So this is okay. This is at the level of the density matrix, so you can think of it as the equivalent of a Fokker-Planck equation. But now I could look at the kind of equivalent Langevin process. So for quantum systems, it's called quantum trajectories. So basically, instead of considering a density matrix, I consider a pure state, psi of t, okay, like in standard quantum mechanics. And I consider all the possible realization trajectories of the system. And I will average over all the possible trajectories, and this will give me back my density matrix, okay? So it's exactly the same thing as the Langevin equation. And what happens in the system is the following. So this is, say, so I have my spin, I have my spin system at time 0, okay? Say I start from some energy here. And so I have two processes. I have dephasing here and processes due to the bath. So what happens is that, okay, this unitary part here, it's doing dephasing, so it's energy conserving, but dephasing during some time, and then at random times, you get projected because of this this part here by SI plus or Z spin. So this is because those quantum jump operators, they are local in the basis here. So you get the impact of those jump operators from time to time, and then dephasing. So you can really see the quantum evolution in this way. And the time between two projections is given by the typical time that you affect to these quantum jumps. So here it was, for example, T1 for a spin flip, or T star for a Z transition. Okay. And so what this means is that, okay, now imagine the timescales are long, which is the case at low temperature. Timescales are very long, so you have a lot of time to dephase. So the system will get projected still in the eigenstates. You have few projections during the evolution, but mostly the system will do its unitary evolution, and it gets projected in the end in the spin basis, the Hamiltonian basis, that is ETH. And in this case, you will expect to have a thermal state. While if you look at high temperature, then those timescales, they become very short, and this means that during the evolution, you will get projected a lot on the local basis. And then you have this, what you expect is that you don't thermalize anymore, is that you get too much projected on the local basis, so that the system localizes, and it's a bit the same idea as the Zeno effect, right? When you're just measuring a lot the system, and you are preventing its unitary evolution by just measuring it. So here it's the bath that measures the system. Right, and since they decrease with temperature, this is what we expect to happen. Okay, right, so I'll try to explain the same idea with the numerics now. So basically the numerics is just, you take this equation, you solve for the stationary state, so you have an equation of this type, L rho equals 0, you take the stationary state, And then you can compute everything in the stationary state, every observable that I talked to you about. Problem is that, okay, it's a many-body quantum system, so I'm quite limited, maximum 12 spin. Right, so the first, I will use two cases, basically, okay. I will take one example, which is basically the same as the two-spin example I know how to deal with analytically before. It's kind of unrealistic example, so this is not what you could do in an experiment, but maybe it helps to understand what's going on. So here I take the same Hamiltonian as before, but I put zero disorder, okay, absolutely zero. So all the spins, they actually are at the same point at energy omega e, okay. So here, obviously, the interactions dominate because they are still interacting, but there is no disorder at all. And I do something that I cannot do in experiments. The microwaves, I only couple them to, let's say, the third spin, okay, to one of the spin, actually the third. And the other are not coupled to the microwave. So of course, in reality, you cannot do that. But what you see, if you do this, sorry, I take timescales of the bath that are fast, so to be in this Zeno kind of regime. And now, if you measure in the steady state the magnetization, the polarization along Z, what you see is that okay, if I take this equation I told you about, so this non-secular equation, the third spin goes to here goes to zero polarization, which means high temperature. Basically, it's very high temperature because it's the microwave is pumping energy towards this spin, while all the rest they stay at the Boltzmann value, so they stay at the normal, as if the microwaves did not exist. Which is a bit strange because of course you are putting interaction. So if you are pumping energy into the system in one of the spins, by interaction they should share the energy, and this is what you see. For example, if you instead look at the secular approximation, what you get is a perfectly homogeneous profile of polarization. So every spin shares the energy and you get the same polarization in the end. All right. Okay, I'm going to skip maybe something that is a bit interesting is that now if you look at this, if you look at the eigenstates of the density matrix, okay, here called lambda, so that the typical states of the system in the end, you can see that with a secular, here I'm measuring basically the average value for each state of basically the spin polarization of some spin, let's say the third spin, but whatever spin. In the secular approximation, you have this value here, which is basically the thermal value. Okay. While if you're doing the non-secular evolution, you see that it's very it's plus or minus 1/2, which means that the states, and it's the same for all spins, which means that the eigenstates in this unrealistic case, the eigenstates of the density matrix are really the plus minus local spin basis, not at all the ETH1, which mixes all the spins. So it's localized due to the interaction with the bath in this sense. Right, and now, okay, sorry, now I'm taking, I will do the realistic case. So the realistic case is a bit more complicated because now I cannot do this trick of putting the microwaves on just one spin. But basically, the important physical thing is that I need to have some inhomogeneity in the system, as I have here, right? I need to have some inhomogeneity of the system to trigger this localization. So I need to create this kind of imbalance. And I did this before by just coupling just one spin. So this is to create a clear inhomogeneity. But in a realistic case, you cannot do that. So what we do instead is that we are saved a bit by the small disorder that is here. So what you do is that all spins are coupled to the microwaves, but they are resonating at some typical frequency, let's say this one here. So this I can tune. And if I tune the microwaves in a good way, basically spins around this microwave frequency will resonate and will be heated up by the microwaves. But the other ones, they are a bit farther in energy and they won't see the microwave. So I'm trying to basically make those spins warmer and those spins will be a bit cooler. Okay. So that's how you do it. That's what happens in the experimental case. And here, so this is really the experimental plot we would like to measure. I'm plotting this so-called EPR spectrum, okay, in terms of frequency. And this is the case where I take low temperature, so 1 Kelvin. So if I do this, you see that you have this typical spin temperature shape, so basically a line close to irradiation frequency here. And this doesn't change if I do the secular approximation or the non-secular dynamics. You see, you get basically the same result. Okay. And now I put a factor 10 in. I put a factor 10 in temperature, so I go to 12 Kelvin. So what does it mean? It means that my time scales. So as I told you, they scale like beta square. So this means that my time scales of the system of the bath are 100 times faster. Okay, and here I get a totally different shape. So the non-secular dynamics gives you a hole burning shape. So you see you have this hole here close to irradiation frequency. So this is typical of something that is more localized. And if I had done this with a secular approximation, I would get still a line because the secular approximation makes you thermalize. So you can see it in another way, is that you can try to fit the steady state density matrix with this ansatz here, which is a thermal ansatz that you expect if the system is thermalizing. So you have some temperature beta S, so this would be the so-called spin temperature. And since polarization is also conserved, you have another quantity, so basically a field. So this is your Gibbs ensemble you should flow to if you are thermalized. And obviously the two parameters will depend on the microwaves, so that's the whole play of the whole game of DNP, is to minimize this temperature here. And if you fit here, you see that, okay, this is the dashed line here, so it fits pretty well the secular one because it's thermal, but you see that it cannot really adapt to the non-secular one because actually, yeah, this shape is really non-thermal at all. You cannot fit it in this way.
So these are data from the numerical solution of the equation.
Yes, I'm basically looking at, before I looked at polarization because it's more physical for us. I mean, it's easy to see which one are low temperature, which one at high temperature, but here this is the experimental feature.
Sorry, the two frequency scale where this EPR spectrum goes to 0 are what?
Sorry, the
frequency scale. You have an edge, a left edge and right edge, where you go to 0.
Yes.
So what are the two?
So the two is that, so you have a typical window of frequency here. It's given by basically, so 93.9 is this omega E, so it's the typical frequency due to which is the...
it's the window of the disorder.
Exactly, and the window here is typically given by interaction and disorder.
Okay.
So, right. And that's why you need the microwave to irradiate at those transitions that are allowed. Okay. If you go outside of this window, you are not seeing it. I mean, the matter is not seeing anything. Right. Okay. Okay. Right. And last thing about this numerics is that if I look now at the entanglement entropy, so it's another measure to see if it's localized or not. Here what I do is that I'm looking at this high temperature case where you have localization. I look at the eigenstates of the density matrix, okay, and so I take them, so let's say I call them n, and I trace over half of the system, okay, then I get a reduced density matrix and I compute the Feynman entropy, so that's typically the entanglement entropy of the states of the preferential states of the system. Okay, and here this is what I plot for, actually here it's not 12 spins, it's 10 spins. So you get, in red, you get what you would get with a secular approximation, so you get kind of high entanglement, while in the non-secular case you see that the entanglement is reduced. So it's not zero. Before, in the unrealistic case, you really go to zero entanglement to purely localize the states. Here the states are not ETH but a bit dressed. And maybe something that is okay. So you have reducing of entanglement, but then the true thing to look at would be the scaling with n. But I cannot do that with 10 spins. So maybe something that is a bit more physical is this plot here. So it's a histogram of the typical value of the magnetization along Z in this sector. So this is the sector where polarization is 0. Okay. And you do the histogram for all the eigenstates, and you measure this typical value, and you see that in the circular case you have something that is peaked around 0, while in the non-circular case it's flat. So this is kind of ETH. This is typical, and this is flat, so it's not at all thermal. Okay. Yeah. So last thing I would like to say is that this thing of kind of Zeno localization. Due to measure to the Bath, it resembles very much, and I think it's basically the same physics that is happening here, to this so-called measurement-induced entanglement transition that has been studied a lot recently. So I'll just do one slide on it, just to mention the relation. So, okay, the setting is a bit different. The good thing about those models is that, okay, they are very schematic models, so with respect to the more experimental one I just mentioned. But the good thing is that here you can do analytically, you can, for example, look at the large n limit analytically, which I cannot do in my system. So these are basically quantum circuits models. The idea is that you try to reproduce the evolution of a many-body system. Let's say spins, you take a quantum spin chain on the line, x, okay, in 1D. And at each time step, you will do random unitary evolution of the spins, okay? So you couple just two spins together, and you draw a random unitary, and you make a unitary evolution, okay, at each step, and then you change a bit your neighbors. So this is supposed to mimic the chaotic behavior, the chaotic evolution of a many-body system. And now, from time to time, in between the measurements, you will with some probability p make a measurement, so project on the local basis the spin chain. Okay, these are the little dots here. And what you see is that if you look at the entanglement entropy of this system, you have a case where at low probability, so low number of entanglement, you see an extensive entanglement entropy. So you are basically doing thermalizing dynamics of this many-body system. While at a large number of so high probability, large number of measurements, you see something that is not extensive at all, and you have a critical transition here, which is of the percolation type, because basically you can see some kind of percolating process here due to the measurement that are separating a bit the evolution of the system.
The plot is L is so it's really numerical simulation with 500 sites.
Yes, but there is also a theory for the critical point, which tells you that everything is like percolation. You have log n.
And how do you go to just because you do 500 sites, but then you multiply by random matrices, so this you can go to large systems.
Yeah, they do about 500, maybe more now. I don't know. Yeah. And they trace over half of the system. Right. Okay. Right. Maybe my last slide before conclusion is that we are now trying to kind of measure this in real systems. So we have a collaboration with experimentalists in Wien. So Denis Korsbach and Ludovica Ipasto. And so what I would like to measure is the EPR spectrum. So far it's not been done, but it's ongoing. And you can see a hint of what I told you before by some indirect kind of measure. You can look at the spin temperature, so the effective temperature of each species, carbon and hydrogen, and you can see this, that at low, basically 1 Kelvin, basically they share the same temperature, and when you increase temperature, you see that here around 4 or 5 Kelvin, there is something that is happening, so they are not thermalizing anymore together, so it's not the same process that is happening. Okay, right, so now so what I wanted to say in this talk, okay, we're trying to explain, so far there was not any explanation of this breakdown of thermal mixing above 5 Kelvin. So we're trying to say that is an absence of thermalization. So it's due to the fact that the vibrational modes become more and more, faster at a high temperature, and you don't have any more dephasing. So we have some kind of many-body Bath-induced localization of the spin system. The crucial thing, I hope I've convinced you, is that well, basically you will never see this unless you go to this off equilibrium setting where you add a drive to create an imbalance in the system, that without this imbalance you wouldn't see anything. But it's still the bath that is doing the projection. It's not the drive that is doing some kind of disorder, it's exploiting the disorder to then be localized by the bath. And to see this, you have to go beyond the usual secular approximation that is used in Markovian dynamics. Okay, and we still see the effect. So it's an effect of kind of strong coupling to the bath, but we still see it in this weak coupling perturbative scheme. And okay, we hope to see this in experiment soon. And okay, it has nice physics, I think, compared to which is relevant. I mean, which is resemblant to Zeno dynamics, and also to this measurement-induced entanglement transition, which is a good thing, because if it's the same physics, I cannot say that everything at large n is still present, because I cannot do a large n with my methods. But here for this transition, we know that the transition is there. So hopefully. Okay, thank you for your attention. Some questions?
Yeah. I forgot, how does the temperature enter in your problem? It's the way in which you rescale the time scale, or is more microscopic?
It enters in the correlation function of the bath. So, okay, it's there. Right, so basically I assume I have a bath at temperature T, okay? Then I have to trace over the bath, and basically the effect of tracing over the bath is contained in those operators here, basically which are proportional to the interaction with the bath. So it's contained in that function here, which I defined a bit later. Yeah, here. So basically it's there. This is the correlation function of the bath degrees of freedom, so let's say phonons here, time t and time 0, which is average on the canonical equilibrium of the bath. So temperature is there. So basically the only way temperature enters is in those two, in this ratio here. So you see here that H has explicit dependence in beta. Sorry, but also T, okay, because it's basically the correlation function of the bath. So that's what defines the time scale. If the bath is fast, then this time scale is short.
Yeah, but in the sense that do you really compute the correlation function of the bath, or you parameterize the time scale as beta squared?
Right. So basically, in the numerics, you see that in this equation, I just need to know what is this, okay, T of omega, which, as I said here, basically it will be, I mean, if it's smooth enough, there will be two time scales. There will be T1 because you are flipping a spin, or T star. Okay, so I just can put input values for T1 and T star from the experiments. That's basically what I did in the simulations. But we tried this. We tried to have a model for this, and this is where we recover this, which is nice because it's basically what you see in experiments. So I don't know if the thing that we did here is the true process that arises, but at least it gives you a temperature dependence that is the one that is observed. But then, I mean, you don't have many experimental data on this, and it's just due to you just take delocalized phonons, and the coupling with the phonons and the system is just due to the fact that you have this the largest Hamiltonian in the system is the coupling with the magnetic field. And the coupling with the magnetic field is basically B times S mu plus some tensor. Okay, so you would expect B on Z and S I Z, but when you have an isotropic medium, you can have a tensorial measure, and this how it's called again, G factor. This G factor depends on space, and then the phonons are in this part here. So you can so that's where phonons couple to the spins, and then you can compute everything. And if you see that if you're just exchanging, which is called direct process, if you're just exchanging one phonon to get omega, then it doesn't work. I mean, it works, but you get temperature dependence that is beta instead of beta square. So it's not really what you see in experiments. But if you go to the higher order process where you are basically exchanging two phonons, then you can get this. But then if you put really the numbers here, you never. I mean, there are people try to model this let's say physical chemistry type of experiment, and no one knows how to really compute from the microscopics. It's a super hard problem. If you get the correct temperature scale, but if you put the numbers here or try to estimate them, you get orders of magnitude off, but no one knows how to do this.
Thibaud, can you show again? Yes, the plot with the entropy as a function of the level.
Yeah, maybe this one. Or in the case of.
In fact, no, some really very naive question. Can you explain whether you have this kind of arcs?
Those arcs?
Yes, what's the reason? So it has to do with spin sectors, or?
Yes, basically. So the way I see it is that I think it's something common when you have a given sector. Is that usually on the edges you have less entanglement. Okay, the way I see it is.
So each sector has a fixed total SZ or something like that? Or?
Yes, exactly. Yeah, exactly. This is so you have all the sector between minus n/2 and plus n/2 basically. So that's all of the sector. Obviously, the 0,1 is the most populated because it's the most degenerate. And why you have this? So I think it's because if I look at the Hamiltonian, where is it? Right. So yes, you see that I have spins with a disorder here. Okay. So basically, I'm in zero polarization. So I have to, let's say I have 8. Okay, let's say I have 8 spins. I could have this, and this would be 0, but I could have any mix of this. Okay, and here, if you take this particular combination here, it has much less energy. So here, in the entanglement entropy, I was ranking levels according to energy, and basically on the edges you have.
So they are ranked by the energy or by the Schmidt value in the.
No, the energy. Here I just took increasing in energy.
But these are eigenstates of rho.
These are eigenstates of rho. Yes.
You can associate an eigenstate of H.
No.
Confused by when you say energy.
Ah, okay. Yeah. Okay. No, but I can look at this. Okay. So rho is. I can decompose it on the eigenstates. And now I just classified them in energy, okay, like this.
Okay, mean energy.
Mean energy.
Okay.
So I rank them, and basically the ones with low energy are the ones where you will have more minuses here, and vice versa. You could flip this, and that's why you have so those would be less energetic, and those would be higher in energy, and basically they have lower entanglement because they look more at this vector. But yeah, it's not something totally clear to me, but it's what you have. And in the middle, in the middle you have combinations of you have things that are more like this, right? And they are more mixed. That's why you have higher entanglement in the middle. But I think that's something we use. That's something usual when you have a smooth sector. When you have edges, edges are a bit special and it's usually a bit tuned, and they have less entanglement. Yes.
I have another question, maybe also online. Actually, I had a question about the experimental side. So you want to measure this APR, this has not been measured. This has not been measured.
Okay, it was measured. Yeah, it used to be measured in the 60s. No, you mean in this experiment?
Yes, in this experiment. I mean, you showed the course of this APR, but these are obtained through your equation, and then I mean, these have not been measured yet.
No, but because there are not many people that can measure this EPR spectrum now. It used to be something that in the 60s in Russia it was commonly measured, and now it's a bit tough to measure it. But
and there are no data. I mean, in the literature, like all the literature.
not well.
Maybe not at the temperatures that you want.
So the thing is that, for example, this thermal mixing is in the NMR community is still something controversial.
Okay.
So I mean, even this is controversial. Okay. So, and what they measure usually it's easier to measure this spin temperature of the species. But this is a much better, much clearer fingerprint. It used to be measured a long time ago, so it's actually a bit crazy that they managed to do that in the 60s. Now you have apparatus that can do it, but no one basically does it. So people in Vienna actually bought a special just to be able to do it. Just that, it's a tougher experiment, and usually they have indirect measure that isn't that far enough.
And do you have a way to use your equation, your approximation to maybe, I don't know, compute some exponents to check that the transition is like percolation in the other model, or is, I mean, just to have an estimate? You seem to say that they are similar physics.
Yeah, physically it seems the same thing, and you have the same thing. You reduce the entanglement, you have a Zeno type of effect, and for me it should be the same physics. Okay. But now, if you want to measure the entanglement, no, I have no idea how to do this, because I have to access basically the eigenstate of the stationary state. I mean, any approximation I can think of will maybe force ETH or maybe force local basis. But as you see in this plot, it's not the local basis. If this was the local basis, you would have zero entanglement. So it's something a bit just like in NVIDIA. So no, I have no idea. But there are other approaches to see this kind of physics. So this one is not maybe the nicest one to look at large level.
Right. Okay, thank you.
Thanks.